Hello, dear colleagues. My name is Ecer Akdemir, and I am working on Australia Forest Wildfire Plume Transport, Integrated Ground-Based Measurements, and Satellite Analysis. I'm working with Dr. Renee Oneja and Dr. William Batty. From November 2019 to January 2020, Southeast Australia faced devastating wildfires. In Australia, this month represents under summertime. So, resulting from highly flammable biota and shortfall of precipitation in Australia, occurrence of wildfires increases, which means that wildfires or bushfires are connected with Australia's ecology and culture. These wildfires affect air quality and emit particulate matter, including PM2.5. And in the past century, the occurrence of wildfire has increased with respect to climate change. The objective of this research is to quantify PM2.5 emissions from wildfire in Southeast Australia, which has occurred during 29th of December 2019 to 4th of January 2020, and coupling suite of satellite data products and ground-based measurements. NASA's WorldView map contains various parameters to determine burned area. One of them is representing burned scars. These burned scars actually represented with MODIS product, which is active fire product detects fires in 1 kilometer pixels that are burning at the time of overpass under relatively cloud-free conditions using a conceptual algorithm. So, to determine burnt area from 29th of December to 4th of January, NASA MODIS maps are used. As seen here, day-by-day changes are represented, and the dark red scars represent burn scar, and neon red scars actually represent the active fire areas. To calculate PM2.5 emissions from burned biomass, represented formula are used. EI is the emission of species I, in this case PM2.5. BI is the area burned at time t and location x. B is the biomass loading at location x. FB is the fraction of that biomass burned in the fire, and EFI is the emission factor of species I. To determine burnt area, NASA's Fire Information for Resource Management System, which is FIRMS, was utilized and created fire points, and these points are put into ArcGIS Pro. As you can see here, purple points represents the fire points for that specific area, and after these points are aggregated via ArcGIS Pro, burnt area clearly determined as meters square. Also, land cover datasets founded from NASA's WorldView map with land cover data and the literature research, other 3 parameters were determined. To compare modeled and measured PM2.5, air monitoring site locations were determined and also added in the ArcGIS. There are 4 different regions which represented 4 different colors, as you can see here, and the red diamonds represent Australian Capital Territory, which is ACT. The blue diamond represents the New South Wales, which is NSW. The purple diamond represents the Victoria region, and the green diamond represents the New Zealand region for our monitoring sites. As seen in the table, total burnt area with respect to dates determined from ArcGIS Pro, and according to burning biomass formula, PM2.5 emissions were calculated as a gram. As expected, burning area and the emission of PM2.5 are directly related with each other. When total burn area increased, PM2.5 emission also increased, and higher PM2.5 emissions is occurred during the larger burning area. For each day, trajectory are determined with respect to high split. To model trajectory, meteorological datasets were founded from high-split archive. Meteorological datasets are selected as NACAR global reanalysis data. The reason of using reanalysis data is that real-time meteorological datasets cause inhomogeneity in the analysis. Additionally, runtime selected as 48 hours to be proper for plume distribution. The other parameters to determine trajectory is starting location. And as you can see here, the starting location is selected as the center of fire areas, and the trajectory is moving different directions and affects different regions. These trajectory lines represents higher concentration area than the concentration distribution. And as you can see in the figures, there are lots of monitoring sites directly affected the highest concentration in the wildfire. Concentration distribution also determined via high-split program. For concentration distribution, addition to mentioned parameters, calculated PM2.5 values from biomass burning used in this model as pollutant group. For each day, this procedure done with respect to PM2.5 values and different starting locations. And as seen here, one of the largest plume reached New Zealand shore within 48 hours and impact huge area. As seen in full array and food stream monitoring site graphs, they started with normal PM2.5 concentrations, which is under the legislation value. Between 29th of December and 31st of December, wildfire plume was not reached the full array monitoring sites yet. And however, when plume reached these monitoring sites at 1st of January, PM2.5 concentrations rapidly increased and reached 1,500 microgram per meter cube for that day. The cause of that much high concentration occurrence is that the location of monitoring site. That monitoring site is near the center of the wildfire. On the other hand, food sector monitoring site located more distance than the flurry from wildfires. So the peak PM2.5 emissions occurred at 3rd of January at 160 microgram per meter cube. To better comparison, one monitoring site is determined where is all of the wildfire plume distribution location. As you can see here, according to Lismore monitoring site, PM2.5 concentrations is not higher than 35 microgram per meter cube normally. Same situation occurs Gunnedah and Rosella monitoring sites. These sites affected less than flurry and food secret because of the wildfire's plume trajectory. Between 29th of December and 3rd of January, wildfire plume was not reached to Gunnedah. Then, plume reached at 4th of January, and PM2.5 concentration reached 120 microgram per meter cube. On the other hand, in Rosella monitoring sites, PM2.5 emissions fluctuated and peak PM2.5 concentration is 110 microgram per meter cube. New Zealand monitoring site much less affected than wildfire plume because of the distance, of course, but still increasing of PM2.5 concentration are seen in the graph. Only 1st of January, wildfire plume reached the New Zealand area, and peak PM2.5 emissions are measured as 40 and 50 micrograms per meter cube. That amount is not as much as higher than the Australia monitoring sites because of the actual distance, because the Australia monitoring sites is located at the center of the fires, but New Zealand is just affected the transported plume. To conclude, estimated burnt area and PM2.5 emissions are calculated, and good agreement between modeled PM2.5 and measured PM2.5 are occurred. PM2.5 concentration increases with plume arrival. And although peak points are changed with respect to plume concentration, increasing clearly seen monitoring concentration in the graphs. And coupling satellites and ground-based analysis provides a unique opportunity to determine downwind air quality for us. In the end, I would like to thank the Turkish government for providing me with support, and thanks to NOAA High-Speed Program for the support it provided. Thanks to a member of North Carolina State University Air Quality Research Group, and finally, thanks to my lovely husband. Thank you for listening to me.